Hey folks, welcome to our last part and where we kind of connect everything together from what we've been kind of going through with our molecular compound section. So in VSEPR theory, we're going to first go through kind of all the rules and have almost a little bit of reference that you could come back to if you needed to check things off, as well as take a look at how these things are drawn. So we'll start off, and what does VSEPR stand for? So it's valence shell electron pair repulsion theory. So the idea that we're talking about the valence shell, the number of electrons in the outside ring, and specifically about electrons and how electrons pair up and how they also repel other electrons. So VSEPR theory is used to predict basically how these molecules look. It's used to predict the shapes of them. And so you've had a little bit of experience so far going through and doing dot diagrams as well as building them, hopefully with the model kits a little bit. And so if we think of bonded pairs, which are those shared pairs of electrons, they make those covalent bonds, or if we think of lone pairs, with the ones that are grouped in groups of two, they're non-bonded or unshared pairs of electrons as negatively charged clouds. These negatively charged clouds are going to repel each other the same way that two sides of the same magnet will repel each other. So to achieve the most stable condition, the clouds must be as far apart as possible in 3D, and so in your X, Y, Z axis, and it would decrease the repulsion force that's there. So basically the amount of repulsion can be kind of ordered, where the force of a lone pair group, so two lone pairs that are connected together, that force would be greater than the force of a lone pair pushed against a bonded pair, and that force would be greater than two bonded pairs that are pushed against each other. So two bonded pairs or two covalent bonds would have the weakest amount of repulsion force, and a lone pair repulsion would have the strongest amount of repulsion force. So in order to determine the shape, the dot diagram has to be drawn first, and then we can kind of introduce those covalent bonds. So there are a whole bunch of rules coming up. I would definitely encourage you to pause the video and to kind of highlight, underline, take down the idea of each of the groups. There's 5 altogether, and I'll show you a bunch of examples kind of throughout the way. I do encourage that if you want to go grab the model kit, you could build them as we go through them. That way you can kind of visually see what it looks like on top of seeing them on the page as well. So the first one we're going to talk about is 2 bond pairs. And so when we take a look at ones that have 2 bonded pairs, we talk about this idea of the central atom. And so our central atom, as a rule of thumb, tends to be the one that can form the most potential bonds. If we look at the periodic table, it tends to be the element that is furthest to the left in whatever compound it is that we're trying to look at. So if we see a few examples, I think that will become a little bit more clear as we go. So they have only 2 bonded pairs. It says that the central atom is going to have a linear shape. Now linear just means straight line with a bond angle of 180 degrees, and you can see that kind of in the picture that's down below, where we kind of have that flat line going. So some examples of this, you can see BeF2, and so if we take a look at the periodic table and match it up with what we see here, BeF2, beryllium is in that second group. It's the furthest one over because fluorine is in group 17. If we take a look at carbon, carbon's in group 14, whereas oxygen is in group 16. Carbon can form 4 bonds, whereas oxygen can only form 2. If we take a look at carbon sulfide, we have the same issue where sulfur is just below oxygen. It's in group 16, and so can only form 2 bonds to carbon's 4. So in those 3 examples, beryllium and carbon would be your central atom. So there's a general formula that these things follow, and in general this is AX2. A just stands for the central atom. X would stand for whatever other element is there as a group of 2. So, and notice it says central atom A from group 2. In a couple of the examples above, you can see it doesn't always have to be from group 2, but if we see a question where we're looking at column 2 and we're looking at beryllium, magnesium, calcium, strontium, barium, all of those are going to end up leading to a linear combination because they can only share two different pairs and they don't have any other valence electrons left over for any bonding purposes. So all of the group 2 elements only have two valence electrons anyway, and they're not paired together as a lone pair. So in general, it has two bonding pairs and no lone pairs associated with just the central atom. You might take a look at them and say, well, fluorine has 3 sets of lone pairs, and that's true, but our external, our X terms, they're not considered in terms of our counting what shape this is going to make. Shapes tend to be determined based on the central atom and what that central atom has for lone pairs and bonding types. So the example that you can see here for beryllium, you can see we start off as a dot structure, we introduce the structural diagram, and then we can take a look at the bond angle as well. And so if you take a second, you kind of build it with the model kits. If you have that in front of you, then you can visualize kind of what these things look like. So our next one is 3 bonded pairs. So molecules that have 3 bonded pairs on the central atom will have a trigonal planar shape with bond angles of 120 degrees between them, and you can kind of see the pictures that show 120 degree marks. So there are examples like BF3 and BH3. Now notice in this case, I mentioned before the leftmost atom tends to be your central one. Hydrogen is the leftmost atom in this case, but hydrogen can only form 1 bond. Whereas if we take a look at boron, for instance, or aluminum or gallium, they'll conform and have 3 electrons around their outer ring, can form 3 bonds. So the one that can form the most bonds ends up being your central atom, okay, which in most cases ends up being the what element furthest to the left, where hydrogen is kind of your exception for the rule. So your general formula for this is AX3, where A represents either an element from group 13, or it could represent another type. Okay, but if I see something from group 13 right away, I can kind of tell I'm going to have a trigonal planar shape. It has a bond angle of 120 degrees between them. Its formula would be AX3, and it would have, we see BP and LP here, it would have 3 bonded pairs to it and no lone pairs. So remember, a lone pair is just those 2 electrons that are connected together, whereas bonded pairs are my bonds between my elements. Okay, they're covalent bonds. So if I have something with 3 bonded pairs and no lone pairs, that tells me that I have a trigonal planar shape with 120 degrees between them. After that, we have 4 bonded pairs, and so we're kind of just moving across the list. In this case, we're talking about central atoms from group 14. So if the central atom is placed at the center of a sphere, then each of the 4 pairs of electrons will occupy a position to be as far apart as possible. And in this case, I should really add in 3D. So it's not like they just stay on a single plane and they go through. And so if you have the model kit, I would encourage you to build CH4 and take a look at it, and you'll really get a sense of how these things repel each other. And so just kind of keep in mind that electron clouds want to push each other apart while still maintaining a little bit of structure. So this results in electron pairs being at the corners of a regular tetrahedron. So in this case, if we have one from group 14 as our central atom, we tend to have this tetrahedral shape. So the angles between each bonds are going to be 109.5 degrees. Examples for this, like calcium chloride or methane or silicon hydride, whereas our general formula is AX4, A being our central atom from group 14. So in this case, they have 4 bonded pairs and they have no lone pairs. So if you take a second and you build this, then it'll make a lot of sense when you see the pictures and kind of how they look. So we start off and we'd have our dot diagrams with our covalent bonds. You can see kind of how they're separated between them. And so they're 109.5 degrees apart. There's a lot of symmetry here where it can be leaned on either side. And so you can kind of get a sense of how these things are structured and how they look. So that's 3 types moving through group 2, group 13, and group 14. As we keep moving over toward the left, we're going to start to introduce lone pairs in. So if we have 3 bonded pairs and 1 non-bonding pair, so there's our lone pair. In this case, we have a trigonal pyramidal shape. And so 4 pairs of electrons will always arrange themselves tetrahedrally around this central atom. But if I have a lone pair on the top, then that kind of adds in this tetrahedral kind of shape, but you get a smaller angle and a little bit different of a look because there's no fourth element coming up on the top. There's no fourth covalent bond. That fourth covalent bond is replaced by a lone pair. So the shape of the molecule is determined by the arrangements of the atoms and not necessarily just by the electrons. So as a result, such molecules are going to have a trigonal pyramidal shape, and due to the repulsion, a non-bonding electron pair is going to require more space than a bonded pair does. And if we look back on slide 1, I've got those kind of in order, and what's has a greater force or greater repulsion force than something else. So the angles in these molecules are 107, not 109.5, as we're in the tetrahedral molecules. And so the examples for those would be NH3, for instance, or PCl3. And as a general formula, now we start to introduce this extra variable here, just called E. So A is our central atom, X is the covalent bonding atoms, and E are the number of lone pairs that are mixed in together. So we have a central atom A from group 15, and we have 3 bonded pairs mixed with 1 lone pair. So if you take a look and try to build something with, say, PCl3, where you're looking for something in terms of the model kits that can form 3 covalent bonds, so it has 3 holes in it for phosphorus, and then chlorine only has 1 available spot, and then if you build them together, you'll kind of get a sense of what these look like. And so some examples of those, it looks like it's kind of raised a little bit from that tetrahedral look, but it has no extra covalent bond coming directly up on it. Instead, it's a lone pair that's there. And so you can get a sense from seeing the dot diagram, or hopefully seeing the model kit drawing of them and what they look like. Then we have 2 bonding pairs and 2 non-bonding pairs. So the 4 pairs of electrons are going to be arranged tetrahedrally, but since only 2 pairs are being bonded together, the surrounding atoms are at 2 corners of a tetrahedron. And so in this case now, if we kind of follow our pathway that we've gone so far, we've done group 2, we've done group 13, group 14, group 15, and so now what happens if we start to get into group 16, where we'd have 2 bonded pairs and 2 lone pairs. So as a result, the molecules in this case, because they have 2 lone pairs on them, they're going to separate apart, and we're going to have a V shape or a bent shape that's going to go. And so the repulsion between the non-bonding pairs is going to result in a bond angle of 104.5 degrees. So the bond angle keeps getting smaller. For each pair of non-bonded electrons, the bond angle decreases by 2.5 degrees. And so you can see some examples that are here, like H2O, H2S, or OCl2. The general formula for this looks like AX2E2, where I have a central atom A. I have my covalent bonding atoms, there's 2 of those, and then I have 2 lone pairs surrounding the central atom. So central atom is from group 16 in this case, and it has 2 bonded pairs and 2 lone pairs. So our popular example from this one tends to be water. And really, it looks fairly simple because it only deals with 3 elements. Just you have to keep in mind that on top of those 3 elements, there's also lone pairs that would show up, that would be here and here, kind of coming out of the page for repulsion. So again, encourage you to kind of build them and take a look at them and see kind of how they look with the model kits. So there's a few things to kind of take away from this. There's 5 different types, so some things to remember. In order to predict the shape of a molecule, you have to draw out the dot diagram for that molecule, and then determine the number of bonding and non-bonding electron pairs. And then you have to compare it with the chart that you kind of now have from the notes, and the shapes will have to be memorized. So when determining the shapes of a molecule with multiple bonds, we have to treat the multiple bonds as if they were single bonds, like 1 bonding pair. So there's kind of the end for this video, and then in the next video we have a bit of practice to go through so you can kind of see how these things could be drawn based on the type of problem that's there. So we'll pick this up on the next video and kind of continue on through our VSEPR theory practice.